My friends, go ahead.
Thank you, Steffi. It's an honor for us to be here, especially I feel so close to DLD, and it's like family, and there's a new family in quantum because the four of us, except for Hildegard, have been following each other. We were in London exactly a couple of days ago speaking about quantum, so it's nice to see you all again. Again, my name is Deborah Bereviches. I'm the lead scientist in quantum computing at VTT, and my esteemed colleagues are Philippe Ernst, who is a senior expert at McKinsey, Hildegard Müller, and let me try to say, who is the president of Verband der Automobilindustrie.
Perfect.
The president of the German Association of Automotive. And then we have Markus Flitsch, who is the CEO of Terra Quantum, and Jeremy O'Brien, who is the CEO of PsiQuantum. So there's a lot of hype and there's a lot of curiosity. It's quite meaningful, as an opening remark, I'd like to say, to talk about quantum in the city of Munich, because I don't know if most of you know, but Albert Einstein grew up as a child in Munich. And quantum requires sometimes a childlike imagination. And also, it's interesting because quantum technology goes beyond what Einstein did in the later part of his life. So it's quite interesting that we are here to discuss that. So without much further ado, I'd like to start with a more general overview. So Philippe, since you work at McKinsey, and the company has done a ton of research on quantum technology sustainability efforts, can you give us an overview of the results, please?
Indeed. McKinsey has looked at quantum computing and applications in quantum computing for the last couple of years. What we see is that given the first fault-tolerant quantum computers, we believe that there will be breakthrough applications specifically evolving around chemistry-type problems. New catalysts, new materials, new routes to reactions. So looking at that and taking sustainability, what I'm very passionate about, you actually see that many of the technologies and climate technologies evolve around this kind of problems. So it was quite clear that we wanted to look deeper into this problem. So together with a partner in the quantum computing space, we actually systematically looked at what are applications that could push climate-relevant technologies and basically pull timelines and accelerate the way to net zero. And in order to do that, we started with a broad world of 150 use cases across all different areas of climate technologies and really looked at what are technologies that face computational bottlenecks. And then we looked at what of these computational bottlenecks could actually be solved by quantum computing in a very different way. And that brought us down to 20 to 30 use cases, roughly, with across 5 different regions, encompassing, for example, battery development, new technologies in hydrogen, material development or material chemistries around direct air capture, potentially cement clinkers.
And Philippe, this is public information, correct?
Yes, this is public information. We have just published an article summarizing these applications and how we thought about this.
Wonderful. So thank you for that great overview, which brings me to the automobile industry, because certainly creating cars with new, more sustainable materials, optimizing routes of cars or taxis or any form of transportation is super important for the benefit of climate. So Hildegard, can you tell us a bit more about what your thoughts are on quantum?
Yeah, thank you very much also for the invitation. You four are the brains and I'm the girl for the use cases. We need this. So we have a huge responsibility in the automotive sector on the way to climate protection, zero emission targets and so on, and also for a life cycle idea that also counts in all these strategies. So when I look at the automotive sector on the future, and on the other side, let me also say, we need a discussion that's not only for the 10% of the public that can decide, do they fly or take a train, do they pay 200 euros more? Mobility is an urgent need for everybody. That means to bring the kids where they have to go to work and whatever it is. So we need mobility solutions in the life practice of the people. So, and then we can look back and what is our need? Our need, for example, is in the new idea of batteries. We need a lot of batteries for the electric vehicles, and I think in quantum technologies could be a huge impact on the battery research. For example, I'm a member of the Helmholtz-Cernet, and in Jülich, here in Germany, there's a huge research, especially for this question. Or a next thing is the fleets. Do we really able to optimize the fleets for buses, for example, in the cities, in the bigger cities, in optimization? And I think quantum computing can help us a lot to learn and to make efficient ways here for fleets. And the third thing I just want to add is the huge idea and my great dream, automotive driving, because there is a great future for this autonomous driving without quantum technologies. I can't imagine. So these is the things we are working on. A lot of my companies are in collaboration in these quantum technology ideas, and so I'm happy to be here and learn a lot of this.
That's great. I realized that I didn't give a little bit of background into what quantum technologies are. So basically, regular computers work with what are called bits, which are strings of ones and zeros, as we all have seen in the movie The Matrix. And they form all the information that we store in our computers. And you can store, a certain amount. And we are getting, in this miniaturization race, we are getting smaller and smaller. But we have been using for 70 years the field effector transistor, and the technology has not changed. And quantum computing is based on quantum physics, which basically tells us that certain things like a photon or certain particles inside an atom, like an electron, can actually have two states kind of at the same time. Basically, there's a small probability. Well, there is a probability. And so these gives way to much more capacity to computers, and it could, right now it's still in its infancy, but if the technology is going to work out, it can give way to calculations that are unprecedented, such as very complex optimization problems, new materials, new drugs, etc. Just wanted to put a little context behind the topic. And what Hildegard mentioned is close to us at VTT because, for example, we care about fuel costs. And a lot of people think there's hype in quantum computing, and so until we have what's called a fault tolerance, so almost a perfect quantum computer, is it really worth investing or getting into the field? And the answer is yes, because way before we get there, there are many, many things that we can do now. For example, if you're a package delivery company, reducing fuel costs by only 3 to 5%, that is just a tiny bit better than the solutions for routes we find now, can have huge impact. Now I'm going to turn to Jeremy O'Brien from PsiQuantum, and you just worked with Mercedes-Benz. This is a major client, and you did a research paper to design better batteries. So can you talk a little bit more about this use case?
Yeah, absolutely, and it's great following on from our fellow panelists here. This is an example of the chemistry that quantum computing will make possible when we have those large-scale fault-tolerant systems that you just referred to. And the situation is that we all have multiple lithium-ion batteries on our person, and those of us who are already driving electric cars are sitting atop this technology every day, and yet no one on planet Earth understands how a lithium-ion battery works. Now, that's a pretty incredible state of affairs. We all have multiple of these systems on our person at any given time, and we don't understand how they work. Yeah. Now, we need better batteries, not just for electrification of transport, but for electrification of our entire economy. Mm-hmm. Mm-hmm. If we're to have a habitable planet into the near future, we will need to electrify our entire economy, and batteries will be a big part of that. Now, we don't understand how those lithium-ion batteries work in the sense that, going into a little bit of the detail, the interface between the electrodes in those batteries and the electrolyte, there's some chemistry that is going on that nobody understands. And what's worse is that we'll never be able to simulate that chemistry on any conventional computer that we could ever build. And to Philip's earlier point, we now concretely understand how to address that chemistry immediately that we have a large-scale, error-corrected, fault-tolerant quantum computer. And so Mercedes-Benz came to us, and they have been tackling this problem, throwing untold millions of dollars at conventional supercompute
How did
capacity.
they find that about PsiQuantum?
Well, I hesitate to do any advertising here, but to your point, and indeed we don't do any advertising, which is part of the point about how they found us, which is that we have been adamant from the start that there aren't useful applications of these small noisy systems that we have today or will soon have in the coming months, that you really need fault-tolerant, error-corrected quantum computing. And so many of our customers come to us having sort of discovered that that's the case by exploring these small noisy systems. And they've heard sort of, in that process that PsiQuantum has been very focused on those, million qubit fault-tolerant systems. So they came to us in that context, having already discovered through their work with supercomputers that this was not going to get them there, through their work in the quantum computing space, that a million qubit system would be the go. And so this is a multi-year project. And to your point about the need to start now, these systems, the world's first fault-tolerant quantum computing systems will be in very short supply. And furthermore, you won't be able to immediately implement your application on those systems. And so the work that Mercedes-Benz have done in collaboration with us is to take the use case, lithium-ion batteries, figure out what algorithm to implement to tackle that, and then optimize that algorithm and optimize the code. And I emphasize that this is a multi-year, large team of computational chemists and quantum computing applications engineers to figure all of this out. And then you get to the point where you're ready to, you're ready to access that system, and along the way secure the access to it. So let me pause there.
Thanks, Jeremy. Okay, we go with Marcus now. And Terra Quantum has done also some technologies and is building a research body to create technologies that can help mitigate climate change. Can you tell us a bit about the work that you do?
Sure. And probably let me start with some client use cases, so real client work, because that, I think, signals that it's not just an academic study, but that's kind of an interest out of industry. And actually, it feels like the automotive industry definitely is an early adopter. We just recently, this week actually, published our work with Volkswagen, one of the very early adopters in quantum actually, where we worked on workflow scheduling in the assembly line. So that is kind of to optimize manufacturing. And the goal, of course, is to do more with less, to do more with less energy, which is already kind of a positive contribution to climate. But to be more specific, one more client we work out of the retail and logistics space, they have a huge fleet of trucks. And one issue is empty miles. So if you drive your truck without luggage, that's not good for environment. So therefore, we have developed a quantum-powered route planning tool to optimize and minimize empty miles with a substantial improvement compared to the classical solutions. And probably two more for a company we work with in the energy sector. It's called Uniper, one of the big German energy companies. One is on make waste more sustainable for energy/biomass power plants. Yeah? So what you have to do is you have to optimize the accuracy of the CO2 and NOx emissions, and that we do with a quantum algorithm. And last but not least, same company, we work on the optimization of the global LNG shipment logistics. Yeah, you might, I mean, wow. LNG is a very important topic these days, yeah, yes. Especially for Europe, those LNG ships. And you might want to ask, well, do we need a quantum computer for that? There's just a few huge LNG ships, but it's actually a very complex problem. And of course, you know, quantum loves complexity. The more complex it gets, the better it is for a quantum computer. And with these things, it is, you have to, e.g., optimize or balance kind of the costs of dirty travel with the opportunity cost of selling LNG with lower methane contents, yeah? So it becomes very soon a very complex problem. So, and these are real life use cases where we work with industry today.
Well, it's amazing because I don't know if the audience knows, but there are very few quantum companies that are already working with actual use cases and trying to solve problems like PsiQuantum and TerraQuantum. And I'd like to hear from you, since the technology is still in the beginning, but at the same time, the urgency of climate change, of combating climate change is here and now. What's the maturity level of the technologies that you are delivering?
Yeah. If I may add to that, absolutely, that's an important question because, e.g., the climate crisis is now, right? Yes. We don't have too much time. We don't have a 5 to 10 years time to wait. So we should use everything which is possible today to do something, yeah? And I think Jeremy rightly alluded to the fact that the native quantum chips are still some years out there until the performance of those qubits is good enough to do meaningful things with it, right? And TerraQuantum actually bridges the gap besides our own native QPU research, which is the hybrid approach. So there is currently kind of a broken compute stack. You have classical high-performance computing, and you have the quantum computing on the software and on the hardware side, right? And the quantum compute hardware is not that performant yet. So what we do is we build the quantum software, the algorithms, but we want to deploy it today for a better for a business performance improvement already today. And that's why we work with virtualized qubits on classical HPC, which means we can deploy the quantum software of the future already today. And we have a very powerful hybrid quantum cloud. And actually, this enables industry to achieve a quantum potential already today.
And this is great. Congratulations on that work, because a lot of the big companies, such as IBM and others, they have the quantum computer physically in their facilities, and they offer the services on the cloud. And actually, I learned, a mathematician and a computer scientist said that there aren't that many algorithms besides Shor's and a few others that are actually written perfectly well to work with a quantum computer. And there's still, you know, a lot of research just theoretically on the algorithms basis. And so it's very important to get starting and co-create, even with this hybrid approach that is so valuable, to find out where the bottlenecks are at these high-performance computing centers. Like, what's not working? How can we speed up this? Or how can we compute many more probabilities of something? We've seen a few very important use cases here: route optimization, new, more sustainable materials. We haven't talked about drug discovery, which is also a huge use case, new batteries. A lot of people here are probably interested in cryptocurrencies. Well, it turns out the RSA security can actually be broken by quantum computers, and so that's going to be a major topic, and actually I think faster, maybe in 5 or so years. You know, many important organizations, banks, governments are working towards securing a new from cyber attacks from quantum computers. So that's important. So you know, we just came from a conference where we discussed a lot about the hype and what's here. How can people in the audience get involved in their companies? How can they figure out how to be quantum ready in their industry or in their company?
Maybe I can have a go at answering that. I think step one is to separate the hype from reality, as you say. And I think you know, there's a lot of hype and there's a lot of sort of bubble and, you know, so on. I would emphasize that, to your point, there aren't a lot of concrete end-to-end worked out applications of quantum computing, but you only need one, and that one is chemistry. And for that alone, quantum computing of the fault-tolerant variety will be the most profoundly world-changing technology that humans have yet uncovered. And to give you a flavor for why I and others believe that, I'm in the habit of provoking anyone who'll listen, including professors of chemistry, with the claim that we can't do chemistry until we have a quantum computer. And it's deliberately provocative, and it's deliberately true in the sense that if you can't simulate the building blocks of the natural world that you find around you, or the building blocks of the human-made world that we have and intend to have, what are you doing? And I think the analogy is that you're doing the equivalent of trying to do state-of-the-art technology and engineering development without the aid of a conventional computer. So imagine a blacksmith's workshop with, hot metal, hammer and tong, and out comes an F-35 aircraft, for example. Yeah. That's what we're doing in chemistry. You mentioned the pharmaceutical industry, which is not the topic for today, but there it's very transparent. There's companies with a lot of money, and if they could make the next blockbuster drug, they surely would. And the best that they can do is to get, an array of compounds, randomly get robot arms to mix them together in the hope of putting something together. Now, Philip mentioned the battery chemistry, but there are many others, green hydrogen, green ammonia, solar cells, you name it. Our world is underpinned by chemistry, and the world that we need to invent, i.e. the one that is sustainable and keeps the planet, to a 1.5 degree or less pathway, there's no more powerful tool than you could have in your toolkit than that large-scale fault-tolerant quantum computer. And the task is to get ready today. Yes. So I think sort the hype from reality, start doing the sort of work that we've just been talking about with fault-tolerant quantum computing companies like the work that Mercedes have done with us. Build your in-house teams, because that will be necessary to do that work, and secure that access to those systems and be ready to deploy it for these, world-saving technologies.
Yes. Wonderful.
May I add, please. Maybe one thing, as you mentioned, hydrogen, green hydrogen, for example. I think you described the open sky, whatever is possible. I think we are now on a point to act and to build joint forces. I think that's the most important thing, to build joint forces over branches. For example, in green hydrogen, we need green hydrogen in every part of industry, and we need to combine it with the energy sector and the needs and so on. And that's one, I think, a really great idea to work on this, because I think it's still underestimated how high is the need on green hydrogen, for example. Yes. And now we live in a time with a lot of challenges, and so we are forced also to be as efficient as possible. And the more efficient we are, the more other areas in the world will follow us. I mean, climate change is a global problem, and what we can here develop in working together and building joint forces can be a role model for the world. And that's also our responsibility, not thinking how, yes, we needed it in Europe to be competitive, to have our standards here and so on, but then it could be a role model. And so we have to think technology open, worldwide technology open. I think that's the main efforts we have to do right now.
And I want to just stop a moment and give an insight to the audience, because that's what I like to do, and see and explain why this is so different than regular computing. I spent many years working in biology, well, the physics of biology, and the way people discover new drugs today is very much like Jeremy stated. We use physics laws that only work for big objects, like Newton's law, the same way I have a baseball. And we pretty much program a molecule like RNA and DNA and proteins and the way they bind with each other with those physical laws. Well, there's a force coming in, and then we have electrostatic interaction. These electrons repel each other because they have the same charge. And so these are very, very big simplifications that obviously can only get us so far. Quantum computing will completely revolutionize that, because now the very computer is going to be made of the very processes that these molecules go through. And it contains a lot of very strange things, like superposition of different states. You know, you can have a coin that has heads and tails, but you can have heads, you can have tails, but you can also have any combination of heads and tails as the coin is rotating. And that's a very strange thing for our minds, right? You also have entanglement, that what happens here and the particle is in China somehow affects action at a distance, what Einstein called spooky action at a distance. And all these things are needed, and I think this is the depth of what Jeremy was pointing at. And so, Philip, you wanted to add?
Yeah, I think in order to illustrate a bit, we've heard world-changing, we've heard large scope. What does that mean? We actually looked into these use cases I mentioned in the beginning, and the impact potential we see is on the order of 7 gigatons per year, right? And that's just 10 use cases we looked at, and to put it into perspective, that's 20% of today's global emissions. So this technology can really facilitate a step change and can be the difference between like the 1.82 degrees if everybody follows their commitments from COP, right, to a 1.5 degree scenario. So it can really be a game changer in terms of closing the gap.
And perhaps I can just add to that. I think as far as what should happen now and the separating hype from reality, although the foundation of quantum computing is very interesting and fascinating, I think it's also a distraction. I'm en route to Davos for the first time in a couple of years, but over the last 6 or 7 years of going there, I've found myself trying to explain how a quantum computer works to people who have 10 seconds to hear you out. And I've come to provoking them with responding, do you know how a transistor works? And don't worry, I'm not going to give you a test on it. You don't know how a transistor works, but do you know how many are in here? What, billion? No, billions of them. And how complicated do you think the system is between a billion things and posting on Instagram yourself at the top of the mountain at Davos, right? It doesn't matter how technology works. We humans get obsessed with worrying about how it works ahead of its arrival. There's plenty of people driving vehicles, electric or internal combustion, have no idea how an internal combustion engine works. They know what to do with it, and you can fly in a plane and all sorts of things. What matters is what you're going to do with the technology, and I would contend that the thing that matters the most is climate change. And you've got to deliver that large scale, utility scale, fault-tolerant quantum computer, and then you've got to deploy it for these applications as swiftly as possible. There's no time to waste. And by the way, to the earlier point, we've got to get on with solving climate change without quantum computing as well. The last thing that I would stand by is any relaxation of people like, oh, quantum computer is going to charge to our rescue. No. Assume quantum computing is not going to happen, get on and solve it. Build a quantum computer as quickly as possible and use that to solve it. That's my conviction.
So we have a couple of minutes left only. I'm just going to add, I beg to differ about that. I really consider an inspiration, the actual workings of technology for a lot of young people. And if we are to educate a whole workforce, just to give you an example, in the US, there are 12,000 jobs advertised on LinkedIn today that have the word quantum in them, and only 2,000 PhDs in physics graduate. If we are to upskill an entire workforce, we need to do it by upskilling and making people passionate about the workings.
I totally agree with you. You can't build a technology if you don't understand how it works, right? But bearing in mind that no one person understands how the chip in that works, but you have to build the technology, which requires
So we're getting the music. Just in one word, I want everybody here to tell me what quantum computing inspires you, or what's your hope for the future. Can anybody
I can
start?
probably start with that. I mean, you discussed it. We expect an exponential speed up of compute power, right? An exponential growth in compute power that says it all. So we are opening up a new era.
Jeremy.
Sustainable.
Sustainable. Hildegard.
And an additional, I think, scaling. That's
Scaling,
also,
beautiful. Philippe?
For me, it's really down to climate change.
Wonderful. For me, it's hopeful. Thank you very much.
Thank you.